Hi, I'm Chang-Bin from Seoul National University. Today I will introduce my work at MERL. Why does music source separation benefit from cacophony? This work was done with my amazing advisors, Gordon Wichern, François Germain, and Jonathan Roux. So let's get started. Random mixing of isolated sources has been used as fundamental data augmentation method for speech or general sound separation. For such kinds of tasks, generated mixtures will sound natural in most of the case. In music source separation, random mixing is also a very powerful training method. However, it makes less sense. Say, if we sample vocal from song A and bass from song B and drums from song C to make a mixture. Will it sound like real-world music? Probably not. Most of the case, random mix is nothing like music. It has inconsistent beat or tonality across each stem. This will lead to the dummy mismatch between training and test distribution of music source separation networks, but so far it worked well. So this raises the question, what do separation networks learn from collections of unmusical random mixes? In this paper, we are going to tackle these questions. First, why do networks trained with random mixes perform better than ones trained without random mixes, in spite of distribution shift? Second, random mixing can make a limitless amount of training data, but performance gains level off. To which extent can random mixing give us a benefit? Lastly, in our intuition, key differences between random and original mixes are whether they have consistent beat and tonality across each stem. How do these characteristics affect music source separation? Before diving into the experiments, let me explain our setups. Here we use TFC TDF Unit version 3, which is one of the winning architecture in the last year's Music Demixing Challenge. And we use the MusDB HQ dataset, which is the standard benchmark data in music source separation, and we follow the 4-stem target separation setup. And also we train models with a batch size of 4 until 470,000 iterations. Thereby, each model will see about 2 million different random mixes during training. This number will be used later, so please keep this in mind. The first topic that we would like to discover is, should we include original mixes at all during training? In this experiment, we introduce a variable p, which is a probability of using original mixes in the sampling process of a data loader. So the p equals 0 model here, you can see the leftmost point in the figure is a model trained with random mixes only, and the p equals 1 model, which is the rightmost point in the figure, is a model trained with original mixes only. Here we compare the p equals 1 and 0.9 models, which are placed in the right side of the figure. We can see there is a 1 dB of SDR gain average over 4 stems, and this means that about 200,000 of random mixes lead to significant performance gain. And as you can see from the left side of the figure, there are p equals 0 and 0.1 models that perform the best here. They showed almost no performance difference, which implies that there's no need to use original mixes for training, and it is powerful enough to use random mixes only. In this section, we compare the training dynamics of p equals 1, 0.5, and 0 models, but we will not go into details here. But we would like to stress that p equals 0 model learns how to separate original mixes without explicitly seeing original mixes. Here we check the influence of the number and variety of random mixes. First, we fix the information of possible random mixes, which corresponds to about 2 million segments from full training data, as you can see in the figure A, and data reduced in half in the figure B. Then we train models using only R% of fixed random mixes. So, for example, from the figure A, 10% in the x-axis corresponds to the model repeatedly trained with 188,000 of fixed random mixes. What we found here is that even 10% of the possible random mixes is enough to train the model equally good as the P equals O model, which was trained with 2 million different random mixes. This trend was found both in figure A and B, and in figure A compared to the P equals 0.9 model from the previous slide, which had a huge performance gain from 200,000 random mixes, we found it is better to just repeatedly use 200,000 random mixes for training. So we guess original mixes may be less informative than random mixes in this section. One more interesting thing that we found here is that 3% of random mixes obtained from the whole training dataset, which corresponds to 90 hours of random mixes, performs better than 100% of random mixes obtained from reduced data pool, which corresponds to 3,000 hours. This implies that the diversity or novelty of random mixes matters for the final performance. Here we did an experiment with modified evaluation sets with timing shift and pitch shift of each stem, so that each test sample can have inconsistent beat and tonality between stems. We found that both inconsistent beat and tonality make separation easier. As you can see in the figures, the amount of shift goes bigger, the scores increase on the same pre-trained models. We also did an experiment with timing and pitch shift during training, and we observed that they make network performance somewhat better, but it still performed worse than just simply using random mixing. Until now, random mix was done on short chunk level, but here we apply random mix on song level to make 86 beat and tonality inconsistent songs. This results in 2.7 hours of new datasets, and on these new datasets we train models without random mixing, following the training method of P equals 1. Surprisingly, models trained with the random song datasets perform much worse than the original songs. When the same amount of data is constructed by random mixing on small chunk level, which corresponds to the R equals 0.09% from the previous figure, the score is about 5.0 dB. It is worse than the models trained with original songs, but much better than the random song datasets. This implies that the domain consistency between training and evaluation matters, especially when data is limited in terms of novelty and amount. So, let me wrap up our presentation quickly. Back to the first research question, we still consider it is not perfectly clear why random mixes are better than original mixes, but possibly it's because of the data diversity. The figure here is the t-SNE result of clap embeddings extracted from random mixes and original mixes, and you can find that original mixes are actually placed all over the random mixes. And for the second question, we found that about 10% of possible random mixes are equally good as 100%, and we also found that the size of data pool where random mixes come from is important. And for the last question, we concluded that inconsistent beat and tonality makes separation easier. Thank you for watching our presentation.